Before we talk about solving quadratic equations, we have to talk about what they actually are, and we need to be able to identify them. So let's go ahead and talk about that now. So here's a simple example of a quadratic equation in what's called standard form, and we'll talk more about what standard form is a little bit later in the course. So we have 2x squared minus 3x plus 1 equals 0, and in this equation the variable is x, but the variable doesn't have to be x. It could be almost whatever we want. It could be y, z, t, w, a Greek letter theta, q, p, s, capital X, and so on. The quadratic term in this equation is 2x squared. The linear term is negative 3x, so we do want to be very careful and make sure that we do include that negative sign in the linear term. And the constant term is 1. So to have a quadratic equation, the quadratic term is required, but the other two are not. You can have a linear term and a constant term that are both 0 and still have a quadratic equation. So in this equation, the 2 on the 2x squared and the negative 3 on the negative 3x and the 1, those are all the coefficients. So a solution of a quadratic equation is a value of the variable that solves the equation. And here's a little fun fact. Every quadratic equation has two solutions counting multiplicities. So what does that mean? Well, one solution might occur twice, and in that case we say that the solution has multiplicity 2. And we'll talk a little bit more about that later in the course as well. And it's also possible for the solutions to be imaginary numbers, for example, 1 plus 2i, things like that. Now, if you're not familiar with imaginary numbers, don't worry about that. I know a lot of you might be using this course to follow along with your own course in school, and maybe your course is not using imaginary numbers. In that case, you could just completely ignore anything I say about imaginary numbers. There is a separate section on imaginary numbers for those of you who need to use something like that, but I do keep it separate just in case you aren't doing anything with imaginary numbers. All right, so the solutions to the quadratic equation above are x equals 1 and 1/2. Because if we plug in x equals 1, or if we plug in x equals 1/2, this equation is going to be satisfied. So let's check that out. If we plug in x equals 1, we get 2 times 1 squared minus 3 times 1 plus 1, which is just 2 minus 3, which is negative 1. Then negative 1 plus 1 gives us the 0 here. So that satisfies the equation. And what happens if we plug in x equals 1/2? Well, we get 2 times 1/2 squared minus 3 times 1/2 plus 1, which is 2 times a fourth, which is 2 over 4, minus 3 halves plus 1, which simplifies to 1/2 minus 3 halves plus 1, which is 0. So plugging in x equals 1 or x equals 1/2 satisfies this equation, which means the two solutions to this quadratic equation are x equals 1 and 1/2. Here are some examples of quadratic equations. Here's the one we just looked at, 2x squared minus 3x plus 1 equals 0. 2x squared minus 3x equals negative 1. This is actually the exact same equation, just written a different way. 1 minus x squared equals 19. 2/3 t squared plus 1/2 equals negative t. Pi y plus 3y squared minus 8 equals 5/2 y plus the square root of 2 minus y squared over 7. So this is a really messy, kind of ugly quadratic equation that has bad numbers in it, like pi and square root of 2. Those generally aren't good numbers to have, depending on what you're doing. But it is a quadratic equation. It satisfies all the requirements. Z minus 5 over pi equals z squared. 5 over pi is also another kind of goofy number, but still, this is a quadratic equation. It satisfies all the requirements and doesn't violate any of the rules. Here are some non-examples. So these equations are not quadratic equations. T plus 2 equals 0. Why is that not quadratic? Well, it's because there's no quadratic term. Remember, we have to have a quadratic term to have a quadratic equation. 2y plus 1, all divided by y squared, plus 2y minus 3 equals 7/2. This is not quadratic as it's given to us because there are variables in the denominator. But we could multiply both sides by y squared plus 2y minus 3, and then we would have this rewritten as a quadratic equation. So we could easily transform this into a quadratic equation, but the way it's presented to us, it's not a quadratic equation. And that's what we really want to focus on, is how is it presented to us. All right, and we also have square root of x plus 5x squared equals 7. This is not quadratic because of the square root of x. That's kind of ruining things for us. So anything with a square root like that is not going to be quadratic. W squared minus 2w plus 4w cubed equals 0. That's also not quadratic because there's a cubic term, 4w cubed. Negative 5t to the negative 2 plus 6t to the negative 1 minus 1 equals 0. This is not quadratic because we have negative exponents. So at a very brief glance, it kind of looks like it might be quadratic, but if we look closer, we see that these exponents are negative, and that means it's not going to be a quadratic equation. And finally, we have x to the 2/3 minus 3 equals negative 2x to the 1/3. This is also not quadratic because we have fractional exponents. So although these last two are not quadratic, they are what's called quadratic type, which means we can use a very simple substitution to transform them into legitimate, actual, real quadratic equations.